In this video, I'm going to use the DS1307 real-time clock chip as a function generator. My previous video, I set it up as sort of a standard real-time clock using Arduino. Now I'm going to use it to generate square waves out of the square wave out pin, which is pin number 7 on the chip. Okay, so the parts you're going to need to do this include Arduino Uno, the DS1307 DIP chip, the 32.768 kilohertz crystal oscillator, and a 10 kilo ohm resistor and a breadboard. I'm also going to hook up the circuit to an oscilloscope and some speakers and a LED light as well. Okay, so real quick, this is the circuit diagram. So it's pretty simple. The DS1307 chip, and in pins 1 and 2 of that chip is where you put the 32.768 kilohertz crystal oscillator. Pin number 3 normally goes to a backup battery. We're not going to use that, so you can leave that floating. Pin 4 goes to ground. Pin 5 goes to the data bus, I2C data bus to the Arduino, which is analog 4 pin. Pin 6 is the I2C clock bus, and that goes to the analog pin 5 on the Arduino. Pin 7 is the square wave out, and that's the one we're interested in. That needs to be pulled high with a 10 kilo ohm resistor. So you just connect that to the 5-volt power rail. Then pin 8 is the VCC in, so that's going to be 5 volts being supplied by the Arduino. Okay, so this is the datasheet for the DS1307, and this table is the timekeeping registers that you read and write to using the I2C serial protocol. For the square wave generator, we're only worried about address 7. We're going to ignore these other ones. Those are for actually setting and reading the clock. So address 7 is 1 byte wide, and there's 7 bits. Several of the bits aren't used, so if there's a 0 in the column, like bits 2, 3, 5, and 6, you always set those to 0. We're also not going to be using bit 7. Bit 4 is the square wave enable bit. We're going to be setting that to 1. That allows you to output the square waves. And then the 2 low order bits, bit 0 and bit 1, based on those values for RS0 and RS1, that sets the frequency of the square waves. So since there's 2 bits, you can have 4 possible frequency values. So then if we go down to this table here, it shows you based on the values, the bit settings for RS0 and RS1, what the output frequency will be of pin 7, the square wave out. So so if they're both set to 0, you get a 1 hertz wave. If RS0 is set to 1, you get a 4.096 kilohertz wave. If RS1 is set to 1, it's 8.192 kilohertz. And if they're both set to 1, you get a 32.768 kilohertz wave. Okay, so this is the source code for the Arduino Sketch, and it's pretty simple, really. We're going to include the Wire.h library. We're going to use that to set the control register on the DS1307. This is the I2C address of the chip. Then I created an array with 4 elements in it, and each of these numbers represents the setting for the square wave address in the DS1307. So recall that if these 2 low order bits are set to 0, that's for the 1 hertz. If it's 0, 1, that's for the 4 kilohertz. If it's 1, 0, that's the 8 kilohertz. And 1, 1 is the 32 kilohertz. And for right now, I'm just going to set this frequency index. I'm going to go through each of those frequencies, but I'm just going to change this value and load it into the Arduino each time. You could probably just set up a button or something to toggle through those, but I'm not going to do that. So in the setup, you do the Wire.begin Then I have a function called init freqIdx1307, and then that's going to write to the address 0. There is a address 0 is the seconds bit, but the highest, the seconds byte, but the highest bit in that field also controls whether or not the oscillator is going to be turned on or off. So I'm going to write 0 means that's going to be turned on. So I have to write to address 0 first, send it zeros, all zeros, and then in transmission, and then it's going to set the frequency. It's going to call that function, and then it's going to set the control byte based on, the index value that I set up here. So it's going to index into that array, and then it's going to write to address 7, and then it's going to send it that control byte, and then in transmission. Okay, so I've loaded the sketch into the Arduino, and this is the 1 hertz square wave being output. It looks kind of odd on the oscilloscope because it's such a low frequency. You usually don't measure or read things down at this level, but we can use the oscilloscope and just verify what we're seeing. So the time per division setting is set at 0.2 seconds. So, and it's kind of hard to see how many divisions this is going across per cycle because it's going so slow, but I think it's like 5. Okay, so you can get the period if you multiply the number of divisions by the times per division. So I'm going to multiply 5 times 0.2, and then you take the reciprocal of that, and it's 1. So 1 hertz. That's what we expected. Okay, so if you don't have an oscilloscope, you can hook up an LED to the output at 1 hertz because the light will flash on for 1/2 second, and then on for a second, then off for a second. So you can check to see if your circuit's wired up correctly, even if you don't have an oscilloscope for the 1 hertz. For the higher frequencies, you're not going to be able to see the flash. It's going to flash too fast, but you can see it at 1 hertz. Okay, so now I've uploaded the sketch with the 4.096 kilohertz frequency, and I hooked up a speaker to the output. Actually, the output of pin 7, the square wave output, is going through a transistor, and then that's what's driving the speaker. So you can hear that audible sound at 4.096 frequency. So if you don't have an oscilloscope, you could hook up a speaker for this frequency, and if you look at the oscilloscope, the time division now is set at 50 microseconds per division. And if we count the divisions, now there's 1, 2, 3, 4, 5 divisions again. So if we do 5 times 50 microseconds, then take the reciprocal of that, I'm getting 4,000. So this isn't a real expensive oscilloscope, but it's really close to 4,096. I guess you play around with this and try to get it closer, but just reading off the screen, it's a good sanity check to show that you're getting what you expect. Okay, so now I'm going to go up to the 8 kilohertz, let's see, and then upload that sketch. And you'll hear the tone change. It'll get a little higher. Yeah, it's kind of annoying. But okay, so now we can set the scale. Okay, so now I'm set to 20 microseconds per division, and now there's 6 divisions, so 20 microseconds times 6. Take the reciprocal of that, and I'm getting 8.33 kilohertz, and the exact value should have been 8.192. So yeah, close enough. Okay, so the next one we're going to go up to the 32.768, and you'll see that, or you'll hear, or you won't hear any frequency, because that frequency is too high for the human ear. Yeah, so it goes away. And then, so we'll adjust this. Okay, so now it's still about 6, it's a little more, maybe, let's see, 6, maybe 6.1 divisions, and we're at the 5 microsecond per division. So if we do that calculation, so 5, and then multiply by 6, I'm at 33.333, or excuse me, yeah, 33.333 kilohertz. So that's close to 32.768. Like I said, you could probably get more accurate, but anyway. And so if you don't have an oscilloscope for this frequency, there's some other things you could do to read it, but I'm not going to get into that. But if you have an oscilloscope, this is kind of a good practice getting how to use it. You could use, obviously, a digital scope if you've got one, or analog, doesn't matter. Okay, so there you have it. To be honest, I don't know a lot of practical uses for using that square wave out pin. I mean, if you didn't have a function generator, or like, I don't know, one of these, and you weren't too particular about what frequencies you wanted to output, you could certainly use it. I mean, you can only do 4, and there's probably ways to split those frequencies up into other frequencies. Probably wouldn't be that hard. But anyway, hope you enjoyed the video.